Hi there and welcome back. This is the continuation of our discussion of query optimization in relational database systems. All right, so let's start at the beginning and look at how query optimization starts off when you submit a query for execution to the system. Of course, there would be some syntactic and semantic analysis checking that the SQL syntax rules are being obeyed and that database objects like tables and columns are being named and mentioned that are indeed present in the underlying database instance, that types are used correctly, that invoked functions are used with the correct signatures, and that these functions have been defined after all. All of these preliminary, very interesting details actually, probably they belong into a course on compiler construction. Actually, SQL can be understood as a rather regular programming language, and analyzing SQL and preparing an internal form of a SQL query, an abstract syntax tree of a SQL query, is really very similar to the construction of abstract syntax tree for your favorite programming language, probably. So let's assume that all of these steps have happened already. What you will then find inside the query optimizer or in a query evaluator of a relational database system is that queries are being normalized. So there is quite some syntactic variety that is present in SQL. And what the system will try to construct is a query that is made up of such select from where blocks, which may be connected by optional union or other set-oriented operators. But these select from where blocks, these would be the basic building blocks of our queries. The system will of course recognize that some of the clauses inside these select from where blocks will be optional. So maybe there is no where clause, maybe there is no grouping. Well, if there's no grouping, there would be no having and so on. So there is some dependencies between syntactic constructs here, but all in all, we will try to generate this normal form of a query. What you will find in the from clause here would either be references to base tables present inside the database or maybe defined as named views inside our database. So this would refer to named tables or maybe to queries that are enclosed in parentheses. So these would be set valued queries that we can iterate over. Okay, so there may indeed be some query nesting present inside the select from where blocks. And as we have discussed in the previous video, well, if it's possible at all, the system would try to get rid of this particular nesting because it suggests particular join orders, processing orders that might indeed be suboptimal. But well, we would start out with these nested form of queries. We would, of course, pre-process predicates and try to construct predicate forms that are normalized as well. So if you look at this particular predicate, it's in conjunctive form where each of the component predicates P are in disjunctive normal form. These normal forms lend themselves to further analysis, to simplification, to factorization, and so on. So we would try to normalize these Boolean expressions as well. Well, we would have other sub-expressions here, which by SQL syntax restriction would be confined to either atomic expressions themselves or maybe subqueries in parentheses that lead to atomic values. That would be this particular part of the commentary on the right hand side. And well, there could be trailing offset and limit clauses where the SQL syntax requires the user to specify literals, integer literals here that specify offset and limit restrictions on the query. All right, all of this would be prepared in a preparatory step before all other query optimization and analysis would happen. All right, so let's look at what query unnesting would mean. So the removal of syntactic constructs inside the query that are enclosed in parentheses, like this query or maybe this particular subquery that might occur in the where clause, for example. Unnesting tries to get rid of these parentheses and to lift the contents of the parentheses up into the enclosing query. Okay, so let's have a closer look at that. Right, so query unnesting. This is all about the removal of nesting inside SQL queries because, well, naively following this particular nesting, parenthesized nesting in evaluation order would probably lead to suboptimal evaluation plans. So we have two queries here, query 1, query 2, and both of them feature nesting. One features nesting in the from clause, as you can see here. So there is a table customers, which would be a base table. That would be one of the possible cases. Or we have a query here, a set value query that is enclosed in parentheses. Well, the SQL semantics say first evaluate this subquery if it's not correlated, and this query is not correlated. First evaluate the subquery. This would give you some intermediate table, which we call T here. Well, and then start or continue with the processing of the top level query, which would be the entire enclosing query here. This is what is being suggested by the parentheses. And as we've seen in the previous video, this can lead to unwise decisions regarding join orders. So the system very early on tries to get rid of these parentheses and to lift the references to the nation table onto the same level as the references to this customer table. So we would ideally end up with a from clause that names the customer and the nation tables as base tables, and then of course adapts the rest of the query to reflect this syntactic change. Once the customer and nation tables are on the same level, well, the nation reference would be found here, then at this particular spot in the from clause. Once they're found at the same level, well, they are subject to join associativity and commutativity reorderings, which could lead to better plans. The same is true for a query like this. This also contains a nested set-oriented query. We are looking for particular customers of particular names here and retrieve their customer keys. This is a non-correlated subquery. The parentheses suggest that this query should be evaluated first to yield a list of customer keys, which we would then use to process the top-level query later on. This is what the parentheses suggest. It might not be the most clever ordering or the way of doing things here. The system will try to get rid of these parentheses as well, lift the reference to this customer table onto the top level and try to construct a two table from clause here that would mention the customer table on the same level as the orders table. Again, that would open up pave the way for further join reordering and optimization at this part. All right, so this is exactly the idea behind unnesting. Lift nested references onto the top level or at least one level higher so that the resulting group of tables can participate in join reordering. Okay, so some of these unnesting cases are rather simple and straightforward. Some of these nesting cases are rather subtle and they lead to some necessary syntactic changes in the original query. All right, so one of these cases I have highlighted on the next slide, where we will have a closer look at what it means to unnest a query of this particular shape, of this shape 2 here. Okay, in general, query unnesting can be performed in several ways. The second way is being shown here on this particular slide. This would be the manipulation of the AST, of the abstract syntax tree that represents the SQL syntax. We would receive as input the original user-defined query, and as output we would generate a different abstract syntax tree that describes an equivalent query, but with a normalized, unnested in its normalized and unnested form. All right, so that would be the unnesting approach that operates on the level of the SQL syntax. There are other ways to implement a query unnesting, and one particular very interesting method to do that is to perform the unnesting on the level of algebraic plan operators. We would start out with this particular query here. We would construct from that particular nested query the initial canonical first plan form for this query, and then would use rewrite rules on the level of the algebraic plan trees to unnest this nested query here and to arrive at a query that just uses plain joins, which then can be reordered. Well, both ways are feasible, but there's one very interesting paper here that is being referenced by this footnote, and you will find it down below here. It's a rather recent paper from like 5 years ago, which has been presented at the German database conference, the BTW conference in Hamburg, Germany, by Alphonse and Thomas, two very dear colleagues of mine. And they've written a paper about unnesting arbitrary queries. So any nesting whatsoever that would be admissible on the level of SQL syntax could also be removed, this paper states, on the level of plan tree reorganizations. I can only recommend this paper very highly. I think it's rather accessible in all its details, and it makes for a very modern approach and very a complete approach to the unnesting problem. Well, while this would lead rather far here, I just leave this literature reference here and would like to briefly discuss with you what it means to unnest this query on the level of SQL. Right, so what we would like to do is to lift all these references to these Q tables, these might be tables or further subqueries, onto the same level as these references to subqueries or tables. All right, once we have done that, here on the rewritten form, all of these would be mentioned on the same level, in the same from clause, if you will, and they would all participate in a large join reordering problem. It would be a large problem, but would also be a large opportunity for us to identify a very profitable join order. Well, to preserve the semantics, when we lift these guys onto the top level, we have to rewrite the query around that. So let's see whether this rewrite makes sense. In the original query, the rows that are retrieved from these first I tables here are being restricted by this P1 predicate. Well, this P1 predicate is also been found here. So any row combination that is being produced by this particular from clause has to qualify against the P1 predicate. Okay, so in the original query, well, rows that were constructed or retrieved using this Cartesian product here in the from clause had to qualify against the P3 predicate. Of course, the P3 predicate is also being found here on the right hand side, and of course it's a conjunctive connection to the rest of the query. Everything that that will be produced on the left hand side of the query had to qualify against P1 and had to qualify against P3 here, and of course we see that conjunction here. All right. The semantics of this in keyword, right? So we are looking for values E2 that we can find in this list of values that is being produced by this inner query here, right? So we are looking for E2 values that match, that are equal to any of these E3 values. Well, this equality, this match, is also being found here on the right hand side of the query. So all of the predicate components, they refer to the predicates and the semantics of the in clause here on the left hand side. As you can see, any combination of values taken from these first I tables here is either present in the result once or not present in the result here on the left hand side. We take this combination of row bindings that we have produced here, and well, either this particular combination can qualify against this conjunctive predicate here, or it cannot. So this combination of row bindings will either contribute a single row here or it won't. To make sure that this is the same here on the right hand side, we need this particular distinct clause, right? So one particular row binding for the first row, for the first I participating tables here may find many join partners, may actually find many join partners in the residual I plus 1, I plus 2 up to Qn tables here. Okay, so to avoid that such binding for the first I tables, right, occurs many times in the result, we will have a distinct clause here, a distinct clause in the right hand side in our rewrite of the query. So any binding E1 or any binding for the first I tables that lead to the relation of E1 is only present once in the result. Okay, so in general we need this particular distinct clause. In the example that we will see in the terminal in a minute, we will see that there are cases that where this distinct clause is not necessary, and indeed the system will be able to detect this. Okay, but in general we will need this here. All right, all of this stems from the fact that indeed on the left hand side, one E2 value could find many matches here in the right hand side in this nested query. Still, each binding for these first I tables would only lead to a single result in the select clause here, and well, the distinct here will make sure that this is the same behavior on the right hand side. Okay, so that might be subtle points, and maybe it's worth pondering these in a minute, just to see that the left hand side and the right hand side are indeed equivalent. This is also here to suggest that query unnesting can be subtle and can be actually error prone, right? So devising these normalization rules, these unnesting rules from left hand to right hand side, these rewrites, they ask for some care when you design these rules. All right. Okay. So well, let's switch over to the terminal and let's see how such query unnesting in both cases, in the case of nesting in the from clause and this case of nesting in the where clause here, this particular case where we use the in keyword, how these are being handled over on the side of PostgreSQL. Okay, so here we are again. We are talking to our TPCH database here. Right, and what I've brought with me here is indeed the very first query that uses nesting in the from clause. So here's a subquery that talks to the nation table, and well, the parentheses suggest that we first evaluate this query, name the intermediate result T, and then perform the join with customer. Right, but as you can see, or as you will see, the plan that is being produced for this nested query is the plan that puts customers and the nation table on the same level, so some unnesting is going on, so that we can indeed perform a join between customer and nation, would be able to reorder that and to enjoy join optimization and the choice of the best join order. So let's see how the plan looks like here. Okay, so you can see the plan is rather compact, and that's also due to my specification of this costs false annotation at explain. So I'm not interested in all the rows annotation, the timing annotations, and all of this. All of this has been left out of the explain output. If you're only interested in the overall algebraic structure of your explain plans, then this could be a very useful parameter that you can supply. All right, so what we can see here is that indeed a single join has been performed. There's no notion of subquery evaluation here, or a notion of let's first perform a sequential scan on nation and then do some projection here before we really process the join. No, the join is the top level operator and it joins the customer and the nation tables. All right, both have been considered to be on the top level. Both can be joined directly, and well, of course, there is the expected join predicate here. All right. What you can see here is that some rewriting in the query has gone on. For example, you can see that the string parse here refers to the row variable t. This is the row variable that ranges over the intermediate result suggested by the SQL query. Well, this has been rewritten into a direct reference to the nation table. Once we have unnested this from query, well, there is no intermediate result anymore. There is no row variable t anymore. All that's left is our scanning of the nation rows n, and this is exactly what we find here. Maybe that becomes clearer if I rewrite this nested query on the level of SQL. So perform the query on nesting in a manual fashion. Normally I won't have to do that, but just to show how the unnested query may look like on the level of SQL, I've prepared this for you. So this would be the unnested query. You can see that the customer and nation tables are indeed mentioned on the same level now. There is the direct join between the two. And of course, I'm referring to the row variable n here, also in the string parse predicate, just like in the plan that we have seen. There is no row variable t, there is no intermediate result anymore. The query has been unnested. And if we look at the plan for this particular query, you will find that it will be identical to the plan for the nested query. And this is an indication that indeed unnesting has been performed by PostgreSQL when it was being presented with the nested query. Internally, the unnested form has been produced before the plan is being constructed. Right, so that would be the plan for the unnested query. If you have a close look at it, it's identical to the plan that has been produced for the nested query. Query and nesting has been performed successfully. All right, and well, I also brought the second query, the query where we've got the nested query inside the where clause just after this in here. All right, and our hope was our rewrite rule on slide 7 suggested that it's possible to lift customers onto the same level as orders here. So I'm sorry. Let me have a sip of water. Yes. But of course, the query around that has to be rewritten. So the predicates have to be taken into account here. They have to be placed in the then top level query and so on. So let's see whether the system can also cope with this variant of unnesting. Okay. Right. The top level is again a single join operator, and the join will immediately join the orders and the customers here. Okay. And no notion of any nesting or whatsoever is remains in that particular plan. Of course, the predicates have been placed. Here is the filter predicate. The join condition has been placed at the correct spot. So all of this has been performed as expected. As you can see, this join predicate here and its equal sign embodies the semantics of the SQL in keyword. So that SQL in keyword and the matching of this one customer key among the customer keys that are being produced by the subquery is now embodied and expressed by this simple equal sign in the join condition. When we talked about slide 17, slide 7, I mentioned this complicated distinct business that was needed to preserve the semantics and the equivalence of the left-hand side and the right-hand side query. None of that is found here in this particular plan, which reflects the fact that the system is indeed aware of the fact that there won't be duplicate customer key values that are being produced by this particular subquery. Customer key is a key in the customer table, so the list of values that is being produced here by the subquery will only ever contain 0 or 1 values. There is no risk of having the duplicated results after we've performed the unnesting here. So there is no need for distinct in this particular case, and indeed no complications regarding distinct, unique or distinct annotations at this particular hash join node are being found. The system is fully aware of this particular fact, that customer key is a key and that there won't be duplicates in the subquery. All right, the picture changes once I present you with a variant of this particular query. It has the same nesting structure, so it's orders on the outside, it's a customer on the inside. We still have the where clause and we have the use of the in keyword here. So the setup is the same, but as you can see now, well, here inside the inner query, I'm returning the C name, the C underscore name column, which is not a key, which is not the key in the customer table. So there might indeed be duplicate C name entries here. That's no problem for the in keyword, as long as we find any match among the C names here. Well, this particular row O will qualify and it will be present in the result. If there will be multiple name matches, again, O will only be present in the result once. Alrighty. Well, once we perform the unnesting here, the system has to take into account that once we place the customer in here in the from clause and perform a regular join, well, then there is the risk of producing duplicate O references, duplicate O's, if they find many join partners in the customer relation. And to accommodate that, let me check that. To accommodate that, the system constructs a variant of the hash join here, the so-called hash semi-join. You see that everything else has remained the same, but the top level operator is now a hash semi-join. The hash semi-join indeed implements this distinct semantics. Any row O that has find one join partner, or 2 join partners, or 3 join partners, will be present in the result exactly once. That's the semantics of a semi-join. Please recall our discussion in the DB2 course if you've ever attended that. All right, so well, duplicate removal is built into this hashed semi-join here, and this implements the distinct that we were mentioned on that we mentioned on slide 7. So the system really performs the correct rewrites here, and unnesting preserves query equivalence. All right. Well, this is indeed the case for the hash semi-join, but even if I switch off hash joins in the system and then post the very same query again, you will see that the system still knows that the semi-join semantics are needed in this particular query. And well, if hash join is not available, then let's use a merge join then, and but use the merge semi-join variant. All right. You can see that, of course, now that we are using merge join, all of the inputs have to be present in the correct join, in the correct row order. All of this is being taken care of, but in particular, the semi-join conserves the semantics of the query after we have performed unnesting. All right, let's switch on hash join again. Okay, right. So much for query unnesting. That pulls up table references out of nested queries into the top level query to form a from clause that mentions a number of tables, which can then be considered for rearrangement, reordering, and so on, regrouping when we perform join optimization. And exactly this join optimization will be the focus of the upcoming video. I hope you'll stay with us for this discussion, and I'm looking forward to discuss this with you. See you then. Bye-bye.